Welcome to the fourth week of this course. Let's look at the PV system design overview. We have looked into the location issues such as the surrounding landscape, meteorological data, and plane of array irradiance. Last week you learned about PV modules. This week we will continue our discussion on PV modules. The standard test conditions are generally not representative of the actual working conditions of a PV module. This is because the PV module output depends strongly on the irradiance and module temperature. These effects will be discussed with the help of the fluid dynamic model. The model is based on a detailed energy balance between the PV module and the surrounding environment. This week you will learn how and why the module temperature and mounting configuration will affect its performance. We will also discuss reliability testing and the IV testing of PV modules in industry. In this video, specifically, you will learn about the electrical parameters of a photovoltaic module as a function of the temperature and of the irradiance. In order to calculate the module performance, it is essential to estimate the effect of the irradiance and the module temperature. You have learned to calculate the irradiance incidence on a module as a function of the angle of incidence. In the next video, you will learn about three models to simulate the influence of temperature. Once the temperature and the irradiance are known, we can derive the efficiency of the module as function of irradiance and temperature. You may remember that the standard test conditions are 1000 watt per square meter, 25 degrees Celsius, and no wind. The module efficiency at STC is equal to the ratio between the power at the maximum power point divided by the product of the STC irradiance and the area of the module. So how do irradiance and the temperature affect the efficiency? Yeah, first of all, we consider the case in which the solar irradiance is constant and the PV module temperature deviates from 25 degrees Celsius. The formulas to obtain the voltage, current, and power parameters at different temperatures are listed here. Usually, in the datasheet of the PV module, the temperature coefficients are provided by the manufacturers. So, assuming that we know the temperature of the module at a certain moment, then the VOC, for example, is re-evaluated from the VOC at standard test conditions by means of a simple linear correlation, where the temperature coefficient indicates the slope of the deviation. The same applies also for the short-circuit current, the maximum power point, and the efficiency. The effect of increasing cell temperature leads to a shift of the IV characteristic towards lower voltage values. Note that the slight increase in the short-circuit current at higher temperatures is completely outweighed by the decrease in open-circuit voltage, and hence the overall effect is a decrease in efficiency. On the other hand, if the cell temperature is kept constant and the irradiation varies, intuitively we can say that the power output of a solar cell decreases considerably with the decreasing irradiance incident on the PV module. However, the quantitative evaluation of how changing irradiance affects the PV module parameters is less straightforward than that for the effect of temperature. This is because solar manufacturers often do not explicitly provide parameters that would allow to derive the PV module parameters at every irradiance level. Thus, as you can see from the equations, the VOC of the datasheet is scaled down with a ratio inside the logarithm, and hence, when we move towards irradiance values that are lower than that at standard test condition, the ratio becomes smaller, and so the VOC. In case of ISC, there is a direct proportional relationship between the standard current and the current that you can have from different irradiance values, and it is given by the ratio between the two irradiances. Finally, assuming that the fill factor of the current voltage characteristic is constant, we can obtain the maximum power point by simply plugging in the open circuit voltage and the short circuit current previously computed. Consequently, the efficiency is obtained from the maximum power point as function of the incident irradiance. Looking at the current voltage characteristic in case of a higher irradiance, we notice the positive effect of a higher irradiance values on the blue line. Here, the short-circuit current increases proportionally with the irradiance, while the open-circuit voltage increases with a logarithmic scale. Finally, when we put everything together and combine the two effects of temperature and irradiance, the final efficiency of the module at a certain irradiance and the temperature can be determined with this equation, where K depends on the different technology employed, for which typical values hold for degrees centigrade. All the other parameters, such as ISC, VOC, and P at maximum power point, can also be evaluated at every level of irradiance and module temperature by simply adapting this equation to the corresponding coefficients and parameters. As the goal is to obtain the PV side performance in terms of DC side yield and to show you how to compute it, we need the DC side power generated by the PV panels before entering the balance of the system, that basically is the charge controller or the inverter. The power generated is a function of the efficiency of the module, which we just calculated, and it is also a function of the panel's area and incidence irradiance. What will come out from this formula is just a power in watt. So now we can define the instantaneous DC side yield as the ratio between the DC power generated divided by the power at STC, which is the one stated in the datasheet. Before we conclude, we stress that this equation is time-dependent, but such a dependency is not explicitly stated for the sake of reporting a tidy equation. So in every moment of the day, a pair of module temperature and incidence irradiance exists. As this is an instantaneous information, it can be used for discrete time simulations. In this video, we have seen that a higher temperature has a detrimental effect on the efficiency, while a higher irradiance increases the short-circuit current. The efficiency of the module was computed as a function of these two parameters, and then we obtained the DC power generated from a PV panel. Lastly, in order to evaluate the performance of the PV system, we introduced the instantaneous DC side yield. In the next video, we will see how to estimate the temperature of the module.